Hello. In this video we will explore the relationship between recurrence and transience of states of a stationary Markov chain and communication between states. For example, if one state is recurrent and it communicates with another state, what can we say about that other state? If one state is transient and communicates with another state, what can we say about that other state? This relates to exercises 16 and 17 in Chapter 1. I emphasize that I'm talking about stationary Markov chain. What I mean is that the transition matrix for the Markov chain is independent of time. It does not change during the process. So, let's first consider Theorem 1.9, which says that if state J is recurrent and state I is accessible from state J, then I and J communicate. Now, what is this actually saying? Let's try to visualize what's going on here. It's always good to try to make some picture in your mind of what's going on. So here I have state J. And you have many states in a Markov chain. And over here I have state I. If I is accessible from J, that means that if you draw the arrow diagram, there must be some path that links J to I. There must be some set of links that goes from J to I. So this is a case where J and I communicate. Of course, J can also go to itself, possibly. All right. Now, we also know that J is recurrent. What does that mean? That means if it goes out, eventually, after some time, eventually it must come back to J. Right? That's a little bit difficult to draw, but have that concept in your mind. If it goes out and visits other state, eventually it's going to come back to J. It cannot stay away forever. Now what this is saying is that if I is accessible from J, then J must also be accessible from I. There must be some other path somewhere that goes from I back to J. And the idea is not so difficult to see, because if the state J is recurrent, that means it always comes back. So if it reaches I, it must somehow be able to come back to J. So it's logically very clear why that has to be. J goes to I, and at some point it has to return, then I must be able to go to J. But the formal proof is in the book. All right? So we'll be using this. Let's go on to the next. Now, exercise 16 in Chapter 1 says that if state I is accessible from state J, but state J is not accessible from state I, then J must be transient. Now, actually, there's nothing more you need to prove. Think about what the theorem above implies. In fact, you can use theorem above and logic to prove this exercise. No more probability is needed. Exercise 17 is a little harder to prove. Exercise 17 says, if state J is recurrent and K communicates with J, then K is recurrent. Now let's see if we can visualize this with a picture. We're given the information that J is recurrent. So let me start with state J. That means every time I go out from J, it will always come back to J. Okay, so no matter what path I take, I might go out on a different path, but no matter what path I take, I will always at some point come back to J. Now K is another state out here, and J communicates with K. That means that J can reach K at some point. It's possible for J to reach K. Right? And it's also possible for K to reach J. All right, now we know that J is recurrent. We know that if we go out from J, we'll return to J. But what about K? Suppose we go out from K. Will we always return to K? That's the question. In fact, the answer is yes. The fact that J is recurrent and the fact that K can be reached from J means that K will always come back to K. One way of thinking about this is if J is recurrent, we saw previously that if J is recurrent, then J is infinitely recurrent. every time it comes back to j, it has another chance to reach k. So the first time it comes back to j, it might not reach k. Second time, it might not reach k. But eventually, because j is coming back to itself so many times, eventually it's going to reach k. All right? So that's kind of the intuition. The chain will always have an infinite number of chances to get back to k from j. All right, so the idea of the proof is as follows. It's always good to have an idea of an outline of your proof to know where your reasoning is going. First of all, we want to show that if the chain starts in k, it will always reach j. Okay, so if I start here in k, it's always going to come back to j. Right? Then I want to show that the chain starting in j will always reach k. So I know if I start in k, it will always get to j. But if I get to j, I will always get back to k. What does that mean? That means if I start in k, at some point I will always get back to k. And that's the same thing as saying that k is recurrent. Okay, so that's the idea. If we can prove these steps 1 and 2, then 3 follows immediately, and 3 is the same thing as saying that k is recurrent. All right, so let's see if we can show these 2 steps. I'm going to give some exercises, and by doing these exercises, you will prove this theorem. Okay, first, you want to show that the chain starting in state k must always go back to state j with probability 1. That's item 1 above. And we'll show this in 2 steps. Show first that the chain starting in state j has a non-zero probability of reaching k. All right, this actually just follows from the definition of communicating. So this is not a difficult problem. So let me choose my sample space as the chain starting in state j. So I'm thinking of all sequences of the chain starting in state j. Now it may seem strange that I'm looking at the chain starting in state j because I want to prove something about the chain starting in state k. But bear with me. So let's go ahead and look at this chain starting in state j and define a partition. This is a partition of omega. Either the chain starting in state j reaches k, or the chain starting in state j does not reach k. So those are 2 possibilities. Okay. And I want to define an event b, which says the chain starting in state j returns to j. So we have our situation where we can use the conditional probability formula. We have a partition, and we have an event. So I want the probability of this event b. The chain starting in j returns to j. Now you know what the probability of this is because j is recurrent. So you can think about what the probability of b is. That's something you know already. What I want you to do is express the probability of b in terms of conditional probabilities. And from those conditional probabilities, you can show that the probability that the chain starting in state k reaches j must be equal to 1. That shows that the chain starting in k always reaches j with probability 1. Next, we want to show that the chain starting in j always reaches k. So let's see how to prove that. Since j is recurrent, the chain starting with j always returns to j infinitely many times. We showed this before. Nj is the random variable that expresses the number of returns from j starting in j. And Nj is always infinite. Now each time the chain returns, there's a non-zero probability, pjk, that it will touch k before returning to j. It may reach k, it may not. But there's a non-zero probability because j and k communicate. In other words, each time it returns, there's a probability 1 minus pjk that the chain does not reach k before returning. So that's called the complementary probability. Pjk is the probability it reaches k. 1 minus pjk is the probability it does not reach k before returning to j. Use this fact to show the probability that the chain starting in j never reaches k must be less than 1 minus pjk to the mth power for every non-zero integer m. I'll give you a little bit of a hint. We know that the chain will return to j an infinite number of times. In fact, it will return at least m times. So consider the first m returns to the state j. and show that the probability that the chain does not reach k during this period is equal to this number. Now that's going to be true no matter what m I choose. The probability that the chain does not reach k before visiting j m times is going to be equal to this value. So that's the first thing to prove. Second thing to prove is this limit. And this you can do using calculus. I want to show that the limit of this quantity is equal to minus infinity. And then I want to show that this limit must be equal to 0. Now there's a very close relationship between this limit here involving logarithms and this limit involving exponents. Finally, show part D implies that the probability that the chain starting in J never reaches K is equal to 0. So you should think about what that means about the probability that the chain starting in J does reach K. Okay, and remember what we're trying to prove. We're trying to prove, in fact, that the chain starting in J always reaches K. All right? So in fact, this statement is equivalent to what we want to prove. You should think about why that's true. So finally, we have the last step. Using B and E, show that the probability the chain starting in K returns to K is equal to 1. That's the third part of our proof here. Okay, so to prove I, you will prove parts A and B. To prove part 2, you prove C, D, and E. And then to prove the final step, step 3, you'll prove F here. Now that will give you a complete proof that if J is recurrent and K communicates with J, then K is recurrent.